Hi guys, welcome to lecture 4, which is on percent composition by mass. In this lecture, we are going to look at some non-chemistry things and some chemistry things and how they all fit together. And then eventually we will learn how to use these to predict different compounds formulas. So first off, let's talk about what percent composition by mass is. It's just what it sounds like. It's when you figure out the composition of a compound by looking at the masses of the different elements. This isn't really a chemistry thing, but we use it in chemistry. The formula for determining percent composition by mass is you will take the part of the compound that you are asking about, and you're going to put it over the whole of the compound. And we're going to do this by mass, so that means in grams. We'll put the part that we care about in grams over the total or the whole compound in grams. And then since we don't like fractions or decimals all that much, we will multiply it by 100, and that will give us our percent composition. So again, not really a chemistry thing, more of just a math thing that we happen to use in chemistry. So here we've got some examples. And so for this first example, what we are going to do is find the percent of oxygen by mass, that's kind of how it'll look as far as words go, of aluminum oxide. So in order to do this, we need to know a few things. For starters, we need to know, there we go. Don't know what happened there. We need to know the formula for aluminum oxide. So that's going to come back. We're back to having to be able to write formulas. So aluminum oxide is Al2O3, right? We got that from crisscrossing the charges. And since I want to know about the oxygen, I'm going to put all of the oxygens over top of the entire compound. So this is what I'm kind of thinking I need to be doing. Okay, but I need to do it by mass. So by mass means that I'm going to take the mass of oxygen times 3, and I'm going to put that on top, and then I'm going to put all of this added up on the bottom. So I know that, let's see, that would be 16 plus 16 plus 16. I believe that that is 1, 2, 3, maybe 48, right? And then aluminum oxide is 101.96 or 97. It's pretty close there. And then all I have to do is divide these two numbers. So 48 divided by 101.96, and then times 100 if I want it to be in percent form. So that gave me around 47.1% oxygen. Okay. And I could do this for aluminum as well if I wanted to, but in this question they only asked me for oxygen, so that's all I did. Okay. This is percent by mass. Okay. And this works no matter what the formula is. In this one, we can see that the formula is a little more complicated. It's aluminum nitrate. It contains a polyatomic ion, but that does not matter. We're going to do the same thing. We're finding the percent of nitrogen over the entire thing. So you have to know how many nitrogens are in this formula. Well, there's 3 NO3s. So that means I'm looking at 3 nitrogens over all of the aluminum nitrate. So again, you're going to need your periodic table a lot in this unit. So we're going to look up our molar masses so that we can add them here. So let's see. Keep losing my pen. There we go. So I know that nitrogen is 14.01. So that times 3. Oops, is that right? Something happened there. Let me try again. Times 3. There we go. So that looks like it should be like 4203. And then I add in the aluminum and look at that, 9 oxygen. So this guy's going to be pretty heavy. Comes out to about 212.996. So maybe I should make that 213. That's a 3. Okay. So 42.03 divided by 213 means that this is 19.7% nitrogen. Okay. Now, What is this good for besides just finding percents? Well, this is what we're leading up to, and we'll get to with lecture 5. But for now, let's just go a tiny step further. So we know the percentage is 97 or 19.7% nitrogen. So the next question would be, all right, so what if I had 65 grams of aluminum nitrate? Then how much nitrogen do I have, right? Well, I have 19.7% of it is nitrogen. So again, not really a chemistry question. It's really asking you just to find 19.7% of the total. So it's kind of like if you count your calories or you count your carbs or you count your proteins, it's kind of the same thing. So here I'm just going to take the 65 grams and I'm going to find 19% of it. So that's going to be times 0.197. That's one way to do it. There are multiple ways to find percentages. Whichever way you prefer is perfectly okay. 12.8 grams, right? I would probably do it this way, but you could also do the 65 grams times 19.7 over 100, right? Or back when I was in school, we learned to use is over of equals percent over 100, and then you plugged in and solved. It doesn't really matter. It's all the same thing. So here we can use that percentage then to find an actual value of each particular element that is in a compound, not just the kind of theoretical percentage, but the actual mass or weight. So it is pretty helpful. Now, the next thing still is a percent composition, but now we're going to talk about hydrates. So we kind of skipped over hydrates earlier. Now they've come back. So to talk about hydrates, we have to back up a second and talk about ionic compounds. Okay, so ionic compounds, remember, are in a crystal lattice. They have that alternating positive and negative structure. And what we know is that because they have that structure of ions and because water happens to be very polar, right? It's got a positive side and a negative side. We know that a lot of ionic substances can actually trap water within their crystal lattice. And when they do that, they are called hydrates. So they're the ionic compounds we've already learned about, but that have water trapped in their crystal lattice. Okay. Now, the compounds that do this in, again, a predictable way. They have a specific ratio of water to that ionic salt. So let's talk about what the compounds look like on paper first. So barium chloride is a good example. Barium chloride likes to trap 2 water molecules for every 1 barium chloride. So if we wanted to write this in a way that you knew that's what was going on, we would write the regular barium chloride, and then we put a little dot here, and then we just put how many waters is stuck to it. Okay. So this little dot is not a multiplying sign, it's just a dot. It's like a spacer, and it's just letting you know that for every 1 barium chloride unit, you have 2 waters. Now this is a very small compound here. This sodium alum, this is much bigger, NaAl and then SO4 too. This particular compound likes to trap 12 water molecules for every 1 alum molecule. So here we put dot 12 H2Os. So if you've ever seen that before and you wondered what on earth it was a hydrate, right? It was a sample that had water locked up in its structure. Okay. Now, the thing that is bad about this is that if I need to have, say, 50 grams of something in order to do an experiment, and I weigh 50 grams of it out onto my little weighing dish from my little container here, right, I would think that I have 50 grams of that substance. But if I have 50 grams of a hydrate, what I have is I have some of the ionic compound, but I also have a lot of water, and I'm not after the water. So one thing that we can do is we can get rid of the water from that compound so we know that we have the pure salt. And that is done by evaporating the water out of the crystal lattice. And that makes the salt what is called anhydrous. So it means that we've gotten the water out of it. And what you're looking at here in this little picture This is the wet copper sulfate, and I don't know if you can see it right here on the bottle. This was from a lab. It says H2OX. So they're trying to figure out how many waters are attached into this copper sulfate. And this is what it looks like when it's anhydrous. So they've dried it out. They've driven all the water off. And we see this a lot, that the hydrated salts a lot of times have color to them, but when they're dry, they're white. So we can drive that water off of them. And then when we weigh the dry dish, we will know that everything in the dish is the salt that we were after. It's not being weighed down by extra water molecules. So how do we do it, right? How do we calculate the amount of water? We're going to do it exactly like we did for calculating an element. Now what you're going to do is you are going to put the part over whole again. But now the part that you're asking about, since it says water, is the water on top over the entire thing. So over the BaCl2 H2O. Okay. So part over whole. So I know what my water weighs, 1802, and there's 2 of them. So that's going to be 3604. But I'm also going to have to now on the bottom add in the molar mass of the barium chloride. So this means I'm going to need a calculator here for a second. Barium chloride is pretty heavy. Let's see, it's 208.23 plus the water. Okay. So this one's pretty heavy. Down here on the bottom, 244.27. Again, times 100 to make it a percentage. And then we just number crunch using our calculators. So 244.27 on the bottom. So that comes out to, this is almost 15% water, okay, by mass. So if I thought I was going to get 100 grams of barium chloride in my sample, really, I'm only getting about 85 grams of barium chloride, because almost 15 grams of it is nothing but water. All right, now same thing, only worded differently, a little more of a look and see, figure out how this looks as a scenario kind of thing here. So here we've got, right, a hydrated salt. So think about the word hydrated. This is our wet salt. It's got our water locked into it. And while it's got the water locked into it, it weighs 3 grams. And then we heat it up until the mass is constant. So that lets us know we've gotten all of the water out and it's not changing anymore. So that means that our dry sample weighs 2.32. So what's left, right? What disappeared was the water. So this was our wet sample. This was our now dry sample. What's the difference? The water that left. What is the percentage of water that was in there? Well, part over whole again. So 0.68 divided by the 3 times 100. This guy was almost a quarter. Wow, 22.7% water. Part over whole every single time. That's what we're doing. Okay. Now, that's the big new thing for today. I am going to back us up a little bit though, because at this point, a lot of people are probably wondering, this says moles on my note sheet. What does this have to do with moles? We haven't done moles at all so far today. And I know that's true. It is going somewhere that's going to circle back around to moles though. And so just bear with me until we get through the end of the week. But where this is going is that if we know that compounds are made of set mass ratios, so for example, if we know that NaCl is always a certain percentage of Na and a certain percentage of Cl by mass, because that is the formula, right? We can use that information, those percentages, to figure out how many grams we have in a sample. And if we know the grams, we can change them to moles. And from moles, and this is what we'll do in the lecture 5, if we know the mole ratio of the elements, we actually can determine the formula from data. So if somebody gives us data that tells us we have a certain percentage of different elements, we will be able to use that percentage data to come up with the actual formula that we're talking about. Okay, and here's just my cute little picture of a mole. And if you've never seen a star-nosed mole, I know this is totally off topic. You should totally look them up because their nose is the weirdest looking thing you've ever seen. Okay, so this is circling back around to moles because we are going to take those grams from the percentages and turn them into moles and those moles into formulas. So as a refresher here, remember that 1 mole of any substance equals the gram weight from the periodic table. That is the conversion and that is the connection that we're going to need this week. Now, just one more little bit of math here just to refresh your memory, right? How many moles are in 63.5 grams of silicon? We will be just doing this one particular grams to moles types of conversion this week. So we start with the given, we bring down the units, and then we put the other part of the conversion that's left on top. Right? Remember that this number comes from the periodic table, which it looks like this is 2809. Okay, just like that. So we need to be able to very easily, without much fanfare, change between grams and moles. And this should have 1, 2, 3 sig figs. So I'm going to call this 2.26 moles of silicon. Going the other direction, 2.5 moles of sodium. Okay. Bring down the given. Well, if the moles are on top, that means the only place left for the grams to go will be on, I'm sorry, if the moles are on bottom, the only place left is for the grams to go on top. Again, without a lot of fanfare, we should now be able to just do quick little conversions like this. Then I punch this in my calculator. I should have 1, 2 sig figs. So this is looking like 58, I believe. 58, 57 grams of sodium. Okay. So these are our 2 things for today. One thing that is new but not really chemistry, finding the percent composition, and then one thing that is completely review, which is turning grams and moles into each other. So what should you be doing now? This is what we should be doing now. There are 2 assignments that go with this half of the week. So we have the classwork, which is the 31.1 post-lecture classwork. There are 10 questions that I have linked for you in CK12 to help you gauge if you have today's content under control. You can use your notes, right? I also linked the CK12 note page for you if you like that kind of thing. I know some of you do. It is not necessary or required in any way that you do the questions that are part of the notes. What you need to do when you go into Google Classroom is you need to pick the one that says 31.1, right? That's the one that you're doing. And then you have two chances on this. So you get 2 tries. If you don't like the score you got on the first time, review, maybe go do the CK12 notes if you didn't the first time, and then go back and try again. Okay. This will be done in class by everyone. This is classwork. Just because it's on the computer doesn't mean that it isn't classwork. It's just I'm not collecting papers. And then the start in class, finish for homework is this, which is 31.2, also already in Google Classroom, which is the empirical and molecular formula, which we have learned before. So again, this is kind of a review. It's going to help you bridge the percent composition new information with what we're going to do with that information to figure out the formulas in lecture 5. This is due before you have class again. Now, you guys know I have reorganized the Google Classrooms so that it's no longer like A, B, and virtual, right? We're not doing that anymore. Now we have basically day 1, which is your 1, 3, 5, 7, and we have day 2, which is your 248, and then you have your everyday class, which is period 6. So each class now has its own Google Classroom, and that way the dates that are on there are specific just to your group, because I know it was a little bit confusing for some of you before, so I hope that the restructuring helps. Okay. So that's it for the first part of the week. And for the second part of the week, we will pick up where this leaves off. So make sure that you've tackled this before we start the second half of the week on Thursday. Don't forget, you can always come and get help on Wednesday during office hours.